I'm Grant O'Reilly. I'm a professor of physics at the University of Massachusetts, Dartmouth. And tonight's speaker is my colleague, Dr. David Kagan. He did his undergraduate at Columbia University, moved to Cambridge, the real Cambridge in the UK for his Ph.D, and then came back to Columbia as a postdoctoral fellow, working with Brian Greene back at Columbia University on string theory. Tonight, David's going to be talking to us about quantum mechanics, which is a timely topic. It seems that quantum something is everywhere, quantum computing, quantum measurements. It seems to be a really exciting new area of scientific research. So, thank you. Before I let David speak, I do want to say thank you to the last round, to Heather, Dave, and the rest of the...
So thank you. This is amazing, by the way. Thank you all for coming. I am blown away by your interest in this topic. Now, I'm not going to refer to my phone very much, but just to tell you, the title that Anne and I came up with, I can't remember it. So the title for today was supposed to be Quantum Computing, a revolution that's sure to teach Schrödinger's cat new tricks and change the shape of industries. I can definitely tell you that I'm more competent to talk about the quantum computing and the quantum side than the industry side, but I'm happy to discuss anything you have questions about. So, and also, I like an interactive, discussion. So I'll start talking, and if something tickles your fancy, if a question pops into your head, raise your hand, ask me the question. If I'm kind of going somewhere, I might say, hang on a moment, but mostly I'm here to talk with you, not just talk at you. So, one last thing before I get going. I just want to really thank Grant. Grant has been a mentor and a real friend. I joined UMass Dartmouth in 2012, and he has been there for me the whole way, and I just really want to thank him. He's a mensch. All right, so let's see. So I think that, maybe the best place to start is actually with maybe the more familiar half of the term quantum and computing. Because we all have computers now. They follow us around everywhere. They're in our pockets. You're holding one right now in your hand, taking a video of it. So actually, I'd like to throw the question to you. What is computing, as far as you know? What do you take that term to mean? Anybody have a... Yeah, go ahead. Yeah, so transforming information, right? Yeah, that's a nice way to put it, right? You get some kind of input, you do some sort of systematic operations to it, you get an output, right? That's it. And it's, of course, super ancient, right? I mean, when the first people realized that these fingers could do more than just, grab a tasty fruit or a bit of nuts, on the ground or whatever, and they said, oh, wait, I don't just gather things with this. I can keep track of them. I can figure out how many I need to feed the family and the kin group and all that stuff, right? They were computing. Counting is the most basic form of computing, right? And as we progressed intellectually, we started, also because we're kind of always looking for shortcuts, we realized that there were ways of chunking operations. So we went from counting, just tallying, to adding, right? Repeated tallying, and we went to repeated addition called multiplication. We figured, we could reverse those operations, subtraction, division. We could repeat multiplication, get exponentiation, right? We can do all these things. And the complexity grows and grows, right? Eventually, we develop the idea of a function or a map that associates an input to an output. And, for a while, as long as the operations are simple, you can kind of keep things going, just informally. But eventually, you need to systematize, as you sort of suggested. You need to systematize how to compute these functions, how to calculate what's going on, right? And so you develop the algorithm, right? Which, if I'm remembering correctly, is a word that's derived from an Arabic term, right? So you develop algorithms, you develop step-by-step approaches, you chunk it down. And we even chunk down our numbers, right? With our fingers, we're used to counting to 10, right? But it's actually also a very old idea, the idea that even just distinguishing between one thing and another, 0 and 1, on and off, that can actually be used as a counting system too. And as a little puzzle for you, you don't have to do it right now, there is a way of using the binary system, where you have 2 digits, 0, 1, to count to 32 on your hand, on one hand. Okay, I'll let you think about how you might do that. It does involve at some point raising the middle finger, so I'm not going to do it here. So you know, maybe you know, if you're being passive aggressive, you can. I was just counting. I got to 5. You know, what do you want for it? So anyway, so that's computation, right? It's as ancient, I think, as human thought, probably. Okay, so what about the quantum side? I don't want to beat about the bush, but I do feel like to set the stage, it's important to know what came before the quantum side, right? So computing is based, like computing, one side of it is pure theory. It's just this business of how do you count better and better. But another side of it is how do you turn that theory into results, reality? Like how do you take these abstract concepts and realize them in using the material that nature provides, right? And that's the engineering side of computation, right? Building computers. I mean, it used to be that we just had a room full of very, very clever people, mostly women, as I recall, doing computations by hand, right? Or with simple devices. Now we do it on these amazingly sculpted, I like to think of the motherboard of a computer as like a sculpture, or like a sculpted fountain. And you've got these microscopic little currents like flowing across it, right? It's like the Trevi fountain, but like in miniature, and you know, anyway, it's just, you know, I get very poetic about this thing. So there's physics that underlies, that translates from the abstract ideas to the reality, right? And up until the turn of the 20th century, our best understanding of physics was what we call classical physics. You hear the term classical, I mentioned the Trevi fountain, I start to think of Vivaldi. I guess he was Baroque. Anyway, I'm not a music person. I mean, I am a music person, but I'm not a specialist. So in classical physics, there is a notion that there's a picture of the world. We may not know the picture of the world, but down to the very deepest level, things are made of particles, or waves maybe. These things interact. They might bang into each other, or they might emit a sort of force field. That is actually a real thing, not just a sci-fi concept. The Earth creates a gravitational field. Okay, and the state of these systems is knowable in principle and predictable. Okay, so a state of a classical system, collection of particles, just flows from, you know, being one thing to being the next thing to being the next thing according to regular laws. That is the sort of clockwork universe picture that was handed down to us by Isaac Newton and his colleagues and rivals and the people all the way up, as I said, till the turn of the 20th century. So what happens at the turn of the 20th century? You know, the Impressionists give way to the Cubists, right? There's all sorts of things happening, all sorts of kind of chaotic, fascinating fracturing of ideas and things in the air. And this is happening in physics too. Is it a coincidence? I don't think so, actually. The physical universe, all the ideas that were under the rubric of classical physics, when we tried to put them all together, started fracturing. It's like a puzzle that you're trying to, you know, you have 3 different puzzles and you're trying to jam the pieces together and they don't fit. And so the picture starts to break apart. Particularly particularly when you tried to apply classical physics to various parts of the microscopic world. People started getting interested in not just matter as a substance, but like what is it made of, right? And they developed this idea of the atom. And then they discovered that that was the wrong word for it, but it stuck. Why was it the wrong word? Well, atom means indivisible, the tiniest thing. The atoms that they discovered actually were divisible. Oh well, you know, my students will understand. We come up with notations and then they're terrible, but we have to learn them anyway. So it turned out when you tried to apply classical physics to study the nature of the atom, like why is it stable, right? You get a nonsense result. All atoms, according to classical physics, can only hold their state where an electron goes around the proton for something like tinier than a nanosecond before it's supposed to collapse. We shouldn't be here, according to classical physics, but we are. That's as big a contradiction in science as you can get. So some folks that you may have heard of, Max Planck, Niels Bohr, and Albert Einstein, they start almost out of desperation, but I think also because they were young and they were trying to really nudge their elders, right? They start to, Einstein especially, who couldn't get a professor position anywhere, right? He was a patent clerk. You know, they start kind of putting out pretty bizarre and wild ideas that are these mixtures of the classical picture. You still got particles doing their thing, but then they start saying, but these particles, they jump. They don't just move continuously. The atoms, the particles, the electrons that go around the nucleus of an atom, they go in orbits, but then these orbits can jump to bigger or smaller radii, right? Bigger and smaller circles, right? And they don't provide an explanation for what's going on. They just say, if we plug that into the math, it works. No one was satisfied by this. This was a major problem. And it all kind of comes to a head in the feverish brain of Werner Heisenberg about 100 years ago. We are in the 100th year anniversary right now of the development of what's called modern quantum theory. And it all goes back to a paper that Werner Heisenberg wrote in 1925. This is a paper, he suffered terrible bouts of hay fever. And, hello. And he suffered from terrible bouts of hay fever, so on a retreat to an island called Heligoland, which is treeless, so he could like get a respite, he had this kind of feverish, you know, just working nonstop on these ideas that were just bothering him. I think a lot of the great advances in physics come from a kind of nervous temperament that hears things that are wrong. It's like the people who are like, there's something wrong on the internet, I have to correct it now. You know, but in this case, it's more productive. So they, you know, he develops a synthesis, but it comes with a major cost. He developed something he called matrix mechanics, and we now call quantum mechanics. But it comes with a major cost. And the key insight that he has is this. When you measure something, you affect the things you measure. It's a very basic idea, right? But his point here was that when you measure something, you affect the thing you measure. And sometimes that effect is significant and cannot be averted. And it destroys whatever you thought you already knew about the thing you were measuring. So, for example, you want to know where a particle is in the room. So you scan around, you ping it, you find it. But if you also want to know how it's moving, can't do it. If you want to know where it is, you can't know how it's moving. And if you want to know how it's moving, you can't know precisely where it is. This is a famous Heisenberg uncertainty principle. And it's a core, it's maybe the core idea in quantum physics, okay? So the upshot of this for Heisenberg, the reason, that might all seem like, okay, fine, so I can't know one thing, I have to choose what I want to know, fine, big deal. Heisenberg says that all of the confusion, all the problem that physicists were having up until then was that they didn't go the next step. Other people kind of realized this. They didn't say, and because of this, physics has to content itself with only being about what can be measured. it cannot ask the question, what's underneath? What goes on when you're not measuring? Okay? What about the things that we can't observe but we think might be there, right? He says we have to banish the notion of an underlying picture of reality. And actually, in preparing this discussion, I went back to a translation of his, he wrote his paper in German, of his original 1925 paper. And it is really striking. I mean, he concludes it with essentially a kind of like revolutionary cry of like, that's it, we're done with like talking about physics in terms of the picture of reality. We just have to focus on what we can predict about what can be measured. That's a big cost. The physical universe before this kind of quantum revolution was a universe where, and theory, physicists and people who study nature thought that what they were learning about was what nature looked like, what nature was like. Heisenberg says that way is going to lead you to madness. We have to just predict the outcome of measurements. And this point of view took hold. His teacher was a physicist named Niels Bohr, who came up with one of the more successful models of the atom. And together they promulgated this philosophy. It's called the Copenhagen interpretation because Niels Bohr had a famous institute in Copenhagen. So anyone who says, by the way, that physics replaced philosophy and philosophy is dead. There's some famous physicists who said that, who wrote it. Some still say it. I think they're very wrong. And the physicists at the time of Heisenberg and Einstein and Bohr, they knew better. They were very well trained in philosophy, actually. Okay, so these ideas, banishing an underlying picture, you couldn't really work with this. So other physicists, Schrödinger is a name you might have heard of. He's famous. He has the cats. We'll get to the cats. He introduced the idea of what is now called a quantum state. So in classical physics, as I kind of threw the word in there, we like to imagine the universe or a system as occupying a state, having a way that it's configured, that evolves from moment to moment. Schrödinger goes, well, it's really useful to be able to at least pretend we can have such a thing. So I'm going to have this thing called a quantum state. It's going to make it a lot easier for us to think about quantum mechanics. And this quantum state also can evolve from moment to moment. But the quantum state is kind of weird. So let me give you an example. First, let's do a classical state. A bit. A bit is the simplest kind of system that can be described in terms of a classical state. It has two of them, 0, 1. That's it. That's all you need to know about a bit. Then you can maybe talk about the rules for how the 0 and 1 changes through time. Okay? That's the simplest physical system I can think of. A quantum bit is a combination of the bit concept having these two states and the quantum concept. So what does the quantum concept do to a bit? Okay, by the way, this is what we call a qubit, which for those of you who know your Bible, it's an intentional pun. There was also a guy named Tony Cubitt. He's still alive. He's a researcher in quantum computation. And some people think that, it's a triple or double pun. I'm not sure how many. It's quantum. It could be a lot of things. Anyway, so the qubit, the quantum bit, it also has two states that we commonly refer to as 0 and 1, okay? Or things that act like a quantum bit. There are lots of things that can act like a quantum bit. But what about this whole idea of, well, but if you measure it, you disturb it, right? Does that mean if you measure the 0, it can flip to a 1? No, it's not quite so straightforward. Instead, there's a whole host of other states called superpositions that mathematically are described as adding the 0 state and the 1 state together. That doesn't mean you get 0 plus 1 equals 1. It's not adding like that. You're adding the states, not the things we call the states, okay? So you add these states, or you subtract them, or you multiply them and then add them, and you do all these mathematical combinations. All of these things are different ways that the qubit quantum state can be described. There are all these different new kinds of states. And it turns out that this really helps with doing quantum calculations. But Schrödinger is extremely disturbed by some of the implications of these quantum states that he came up with. He tried to heighten the contradictions. He tried to like make the picture as bizarre, like he wanted really to get through to people how bizarre the picture was. So he imagined a box that leaves, like it isolates everything from in the inside of that box is isolated from the rest of the universe, okay? And inside the box, he places a cat. I don't know, maybe he didn't like the cat, I don't know. And inside the box with the cat, he places a vial of toxic gas, but it's stopped up. And he sets up a device that depends on the state of a particle that acts like a qubit. The particle can decay or not decay, okay? On or off. But it's a quantum particle, so it can also be in a state of some kind of superposition, a kind of quantum mixture of decay and not decay. And what he reasons is, and you can do the math here actually, he reasons that if the particle decayed, the vial would break, the gas would be released, the cat would be dead. Sad. I don't like it. If the particle does not decay, the vial stays closed, the cat is alive. If the vial is in a quantum superposition state, which is some weird quantum combination of decaying and not decaying, then this actually does something really weird to the cat. The cat becomes a combination in some sense of experiencing the vial not decaying and being happy and being alive, and experiencing briefly the vial breaking open and dying. So this is the famous, the cat is alive and dead, okay? And he says, you know, of course when you open the box, you're only going to see one or the other of the options. We don't see cats that are in superpositions. We see cats that are alive and we see cats that are dead, okay? So he goes, what do you make of this, Heisenberg, you know, and Bohr and so on? And they say, look, you've committed the grave sin of trying to picture an underlying reality, right? This was their go-to move, right? You cannot, when the box is closed and this quantum state is in a superposition, you cannot picture what's going on in there, okay? It's not that the cat is both alive and dead at the same time. That's not right. That is a picture. That's not allowed. It's that we cannot say a word. By the way, they were very influenced by philosophers like Wittgenstein, who said the thing of whereof one cannot speak, one remains silent. Right? This is a philosophy called positivism, and it had a big impact on Heisenberg and Bohr and some of the physicists in that milieu in that time. So Schrödinger finds this unsatisfactory. Einstein finds this very unsatisfactory. The situation is a total mess, philosophically. But Bohr and Heisenberg kind of bulldoze their way, and most people who get trained in quantum physics, even to this very day, are learning the Copenhagen approach to quantum mechanics. Okay, if this is a bit of if you're detecting a little bit of frustration about this, well, my main area of research nowadays is like interpretations of quantum physics and why Copenhagen just doesn't cut it. But that's not what I'm here to talk about today. So we've got an introduction to classical states, quantum states. What about how do we circle back to computation? Well, remember, computation is about taking abstract ideas about counting and implementing them in physical systems. We call them computers now, right? But we, sometime even before the actual computers got built, we developed a whole new theory of microscopic reality. Or, well, we can't talk about reality, but at least how microscopic things can be measured, okay? This is quantum theory. So the question is, does that have any implications for computing? And the answer is yes. In the 1980s, researchers started thinking about what if we replaced bits in computers with qubits? What if we had computers based on this idea of these quantum bits that can be on or off, but they can also be these weird quantum superpositions that Heisenberg says we're not allowed to try and picture. Can we do anything with that? And the answer is, yeah, you can actually. One of the astounding things you can do with a quantum with quantum bits is if you have a pair of them, or more than a pair, you can set them up in these states, okay? So think about a pair of just regular bits. How many different values can you have? 0, 0, 0, 1, 1, 0, 1, 1, right? Well, quantum bits, a pair of quantum bits can be those states, but they can also be superpositions. So for instance, you can have a combination of 0, 0 plus 1, 1. And that means you can have your quantum bit, and your friend can have their quantum bit. And how do you read what is supposed to happen when you measure your quantum bit? Well, when I measure mine, there's a 50% chance I get 0, a 50% chance I get 1. When you measure yours, there's a 50% chance you get 0, there's a 50% chance you get 1. We can be very, very far apart at this time. What's interesting is when we come back together and compare our notes, we discover that despite the randomness in the outcomes from our measurements, let's say we do this a lot of times, every time your quantum bit measurement matches mine. So there was randomness on my end, randomness on your end, and yet some kind of coordination across distances, okay? This is very eerie, very spooky. And this actually was an idea that Einstein came up with as a way to prove that quantum mechanics couldn't be right. Well, the Nobel Prize a few years ago, I guess, showed that he was wrong about quantum mechanics not being right. So this is a state called quantum entanglement. This is a configuration called quantum entanglement when these particles, they can be measured, their states are random, and yet somehow coordinated. So what can you do with this quantum entanglement? Well, what you can do is set up a kind of form of quantum parallel processing. You can essentially have a computation where the computer runs through all possible permutations of the answers by having a superposition of them all. Now, before you say, oh, so it's doing all the computations at once, there's a sense in which it is. But at the same time, at the end of the day, you have to do a measurement. And that measurement will bring you back to one specific outcome. And it's only if you can set certain things up to delicately cancel out in these computations, I'm sorry, I have to be a little vague about this, that you can get useful results. But these useful results, while rare, are extremely profound. So a quantum computer, using these effects of quantum entanglement and quantum superposition, a quantum computer that, let's say, was supposed to search a database, right? Everything about our lives, by the way. Phones are full of databases. Our names are in databases all over the place. There's all this data mining that goes on, all the machine learning, all this artificial intelligence stuff. It's all based on gathering data and training the machines on data and searching and finding and connecting and making patterns. There is an algorithm called Grover's algorithm, and I'm really trying hard not to make that Yoda voice that Grover had. So Grover's algorithm, named after an actual person, not the blue Muppet, is an algorithm for searching a database using quantum effects that speeds up over any known classical non-quantum database search method. Okay, it's not a huge speed up. Basically, if it takes you 100 seconds to search a database using standard methods, a quantum computer, a theoretical quantum computer that could do Grover's algorithm, can search it in 10 seconds, approximately. Okay, that's a decent speed up, 90-second speed up, but it's not unbounded. Okay, a more startling result is something called Shor's algorithm. Shor's algorithm involves something that you might think, why would that matter at all? It involves prime factorization. How many people remember, just a show of hands, no embarrassment, no judgments here. How many people remember what prime factors are? Yay, that makes me happy. I promise no judgments, but it still made me happy. So prime factor, right? Like every number, it has like a code that goes with the number. You can break it down into these little primary smallest numbers that can't be broken down any further by multiplication, right? The prime numbers, 2, 3, 5, 7, 11. I'm very bad at arithmetic, so don't push me. Ask me about Grothendieck's prime. It's a bit of a digression, but I'm going to plant a question. Ask me about it later. So you can break these numbers down into these factors. Now it turns out that multiplication is a pretty quick process. Multiplying two prime numbers, fairly quick. Certainly for a computer, very quick. If I give you a really large number, and all I tell you is that it has two really big prime factors, that's a very hard problem to solve, figuring out what those prime factors are. This is what's in computer science and in encryption theory is called, or cryptography, it's called a one-way function. It's easy to compute one way, it's really hard to do the other. Shor's algorithm is the first quantum algorithm, it's the first algorithm we know of that can compute pretty rapidly the prime factors of a really large number. Why does that matter? Well, it matters because pretty much all of the security, all of the encoding of your data, you're on your phone right now, right? You're taking a video, and that video is being encoded. Maybe you're going to stream it somewhere later, right? All that encoding to keep it private, to keep aspects of it private, your credit card information when you maybe went out and bought a tomato just in case this was a bad talk on Amazon. You're going to throw it at me later, right? You trusted them to take your credit card info and not leak it out. Sadly, there have been hacks, right? But that's a different story. All of that is guarded by a procedure that is resting on the difficulty of prime factorization. So Shor's algorithm, a quantum algorithm, kind of debases that entire method of securing the internet, securing your bank data, securing your privacy. Don't worry, I'm sure someone's thinking about how to fix it. There's a lot more I can talk about, but I don't want to just talk and talk and talk. One thing I will say is there are quantum approaches to dealing with this problem of prime factorization, and there are actually non-quantum approaches as well. So I guess the upshot of this little taster, is computation is deeply linked to the history of human thought, and it's deeply linked to the history of humans wanting to take thoughts and turn them into realities. Okay? Up until the 1980s, all we had was a theory that used the classical ideas about how information works. Quantum theory has given us new ways of structuring and understanding the behavior of information in actual nature. So if we got all these quantum algorithms, why aren't they taking over? I mean, ChatGPT came out like 4 years ago, and now every college professor has nightmares every night. I don't know how much of your world it's changed, but it's certainly changed mine and Grant's a lot. And maybe my students too. They're smiling, they're very happy. No, it's really cool. I mean, I love it, despite the headaches. So that came out 4 years ago. We're talking about ideas that people have been thinking about since the 1980s. Where is the revolution, right? Wasn't that the title of the talk? The answer is quantum computers are really, really hard to actually build. There are quantum computers. Companies like Google and IBM and Amazon don't want to leave anyone out, but I'm going to leave someone out. Countries like, I don't know, China. I've heard of that one. And the United States, I think that's another one. At least until recently, they were competing, right, to put more and more funding into researching how to build a quantum computer, how to work quantum computers. There's been a lot of progress, but it is very hard. And the reason it's hard is because, essentially, it's really hard to see Schrödinger's cat be in a superposition state. Superpositions are extremely delicate. The tiniest particle of light hitting your quantum system can, remember, Heisenberg told us, a measurement interaction with a quantum system will irrevocably change that state, right? So the tiniest particle of light hitting your quantum system can destroy your computation. This is the fundamental challenge. And this is why, while the promise of revolution is like, it feels really imminent, there are still some major hurdles and challenges on the engineering side. Okay, so I think that's an overview. Hopefully it's seeded a lot of questions for you. And at this point, I'm happy for you to ask me your question. Thanks so much for your attention. The question was, is there some way to visualize a superposition? Can we make some sense in our minds? Is there some way of getting a picture in our heads, even like a cartoon picture, of what it means to take the 0 state and add it to the 1 state in this kind of quantum way. And I mean, that's the question that like every physics student who take quantum mechanics, I don't know, is that the question that every physics student who take quantum mechanics asks at some point? Oh, there we go.
So stupid. The question was, is there any way to...
Yeah, the question is, no, the question is the question, can you visualize a superposition, something that crosses your mind as you're being taught quantum mechanics? They're nodding, yeah. What was the point of coming here if you're not going to be my plants? I mean, come on, no. Heisenberg would answer your question with a very stern 9, you know, like, you don't visualize quantum states. There's no way to understand underlying reality. But I think the mind rebels at that, right? You have to have, 4 years of undergraduate training and then another 4 or 7 years of Ph.D. and have that kind of thought beaten out of you before you go, no, of course you don't want to picture it. What are you, crazy? But I will say this. So to answer your question, there is no consensus universally agreed upon answer to your question, which is really stunning. Quantum mechanics is 100 years old. When Newtonian physics was 100 years old, yeah, people argued about whether materials were made of particles or were they made of waves, right? There was a kind of debate about this, but both of those you can picture in your mind. Quantum physics is 100 years old. I have no excuses. We just haven't turned that assignment in. It's very late. What there are a number of what are called interpretations of quantum theory. The Copenhagen interpretation is one. But most people who get into this business of trying to come up with pictures, and that's, by the way I like to think about it. An interpretation is an attempt to answer your question in a way that goes beyond Heisenberg. Most of the people who get into interpretations are not happy with Copenhagen, because that's the textbook interpretation. They're kind of rebelling. Okay, so one kind of intuitive way to think about it that I personally reject is you think of the 0 plus the 1 as meaning it's both at the same time somehow. It's both 0 and 1. Like, you kind of almost imagine it like superimposed. But when you really, the reason I don't like that picture is, well, there are deep technical reasons I don't like it, but there's another reason, which is when you just really try and think about what that means, it's unclear that it got you anywhere. I mean, it's kind of, I don't know, it's kind of faking you out, right? There are some interpretations that are very exciting sounding. The 0 plus the 1. Well, okay, so let's say I go and I do a measurement. This is another famous problem of quantum physics, right? Heisenberg described what we can know is what we can measure, right? And that's what physics needs to be about. But then you go, Professor Heisenberg, what is a measurement? And Heisenberg goes, well, it's the thing you use to get information. Yeah, but isn't it like, don't I have to build a physical system? And it does, and anyway, it's another problem. It's called the measurement problem in quantum physics. Again, 100 years old, still fundamental problem in the very basic bones of the theory. By the way, before you get the idea that quantum physics is wrong, I want to step back for a moment and say, all the criticism I'm giving is despite every experiment ever designed confirming quantum physics. Every experiment, all the technologies, they pervade our society. They pervade our lives. They're all based on quantum physics working, okay? So these problems, these philosophical issues of what is a superposition, how can you visualize it? So I just want to say, to stick up for quantum theory for a second, yeah, we may be 100 years late on certain things, but we've done a lot, okay? And it's translated into maybe not quantum computers that can work just yet, but LED screens and quantum dot displays on your super fancy TVs, and all sorts of aspects of understanding chemistry and so on and so forth. So to get back to the philosophical thing, so there are some other interpretations. So one is, you've got a system in a 0 plus a 1 state. You go to measure it. So this interpretation tries to get around the measurement problem by saying, oh, well, what happens is you become part of the superposition. So there is a copy of you. There's an entire universe that involves you seeing the measurement 0 come up. And there's another universe that splits off that sees 1. This is called the many worlds interpretation. I see you shaking your head. I also shake my head. Well, I mean, so the idea is, it's actually kind of, does anyone know the TV show Community? Anyone remember the TV show Community from ages ago? I guess it's ages ago now. Gosh, it's time. That would be a different talk about the nature of time. Anyway, in that show, they play a game with some 6-sided dice, and the episode splits off. Every time they get one thing, they go into a different reality. Like, what if the die landed 6, and they did, right? So it's kind of similar to that idea, this idea of many worlds. You do a measurement, and there is a version of you that sees one outcome, and there's a version of you that sees another. I mean, there's lots of movies, I think, that have had this, concept. It's an interesting idea, and it's actually helped develop certain aspects of quantum theory. Like, people have made advances in quantum computing by thinking in terms of this interpretation. I think there are problems, but I'll reserve judgment for now. Yeah. So Grant's question is a question of, okay, so we have this theoretical quantum algorithm. It's sitting there. It's waiting to be implemented, right? But we don't have the quantum hardware to do it. It's a little bit of a lie. People have done it, but they've done it for numbers like, 15. Okay. No, I think the state of the art is actually better than that. But they're certainly not numbers that any of us would have a hard time prime factorizing, as far as I know. So when will quantum computers overcome the issues of the delicacy of quantum states getting interfered with by the environment? Well, let me say a couple things about that issue a bit more, and it actually connects to this thing of, like, why don't we see superpositions in nature at all? So there's an effect called decoherence. So when a quantum system, when a qubit is in this superposition, 0 plus 1, we call that a coherent state of the qubit. When that breaks, when the qubit is forced to go into the state 0 or the state 1, that's called decohering. And and it's actually connected to this issue of measurement. So since Heisenberg, people have come up with much better answers about what measurement is kind of like. Again, it's still a measurement problem in quantum mechanics, but we've made advances. Measurement is a kind of interaction with a system. And it's an interaction that reveals information about that system's state to a broader, big environment, like the air in this room, or the bath of light that pervades us from the Big Bang. That's actually enough of an environment that those particles can interact and get information about your part. So this is what we have to deal with, right? As I said, the slightest photon can come and decohere this quantum state. So Grant's question is, well, so when do we beat this out? It sounds pretty insurmountable. Well, another set of algorithms have to do with what's called quantum error correction. I actually feel like backing up. There are particles bombarding us from space right now because we're being invaded. No, we're not being invaded. There are just particles that just go very fast and make it through the atmosphere and shower down on us. And more importantly, they shower down on our electronics. And they are flipping bits at random in our electronic devices. Yet our electronic devices don't get messed up by this. Why? Because they have built-in redundancies called error correction codes. And these error correcting codes allow you to take chunks of bits, and if one of them randomly flips in a way that it's not supposed to, they can correct it back because of the information about the surrounding bits. I'm simplifying. Bless you. So people figured out a way to update this idea to the quantum world. It's much more complicated, but the basic idea is the same. Quantum error correction is about correcting the kinds of random errors you might get, in particular from random particles interacting with your quantum system. I got it. So So the real answer to your question, Grant, is I'm not 100% sure. I think we're better. I think odds are we'll get it before fusion. I know. I think that we're already seeing experiments being done. Google publishes every year a new experiment on the next level of error correction. IBM and Amazon, all these companies do this. So I don't know. I don't think it's outside the range of possibility to see it in the next 10 years. Yeah, go ahead. It's a ChatGPT question. You maybe know more than I do about ChatGPT. I think so. So the question was, when you're interacting with ChatGPT, if you don't mind, I'll try and simplify. Is it kind of taking your data as you're interacting? And I think it's safe to assume that yes. That's part of the business model. So you should definitely not share. Like if you're a teacher, I wouldn't write private information about students. And there's a conservative answer, which is just don't share anything that you wouldn't want shared with the world with ChatGPT. I think maybe there's a moderate answer that it's like, well, maybe within reason, as long as you're not like literally giving it the text of your book and you're just asking questions, I think it could work. But yeah, I'd be careful, Yes. The question was, is what I've been talking about with regards to quantum computing, does it, with this idea of quantum entanglement that I kind of touched on, does it apply to questions about communication, if you don't mind my summarizing, right? Securely over long distances. And the answer, I think, is yes. That's actually one of the motivating use cases, right? And actually, there's a very deep connection between communication and computation, right? In the 1940s, Claude Shannon developed the modern theory of communication, right? And information, right? And again, it's about encoding, it's about processing, it's about transmission, right? What is a computation? It's in some sense a transformation of data across time, right? What is a communication? It's a kind of transformation of data across a distance, right? So there's an interesting kind of relationship between these things. Yeah, if people don't mind, I can give a conceptual description of an example in which quantum communication ideas have actually been implemented. That's actually, weirdly enough, easier to do on the engineering side, though still baby steps. When you want to pass a secret message to someone, I've already mentioned the idea that you can encode it using prime factorization methods, right? The most secure way to transmit secret messages to a friend is to prearrange that your friend and you have like a pad of paper that has a code alphabet, a key, what's called a key, okay? And you both have the same thing, okay? You've distributed it somehow. And now you can use the key to encode your message. That way, when you transmit your message and your next door neighbor who kind of has it in for you wants to get the dirty gossip about you, if they intercept, it's a big scrambled mess. They don't know what it's saying. But when your friend gets it, they can use their version of the key to decode and to read the message. Maybe you're asking for some personal advice, right? So one important step in this process to keep it secure is you only use the key for one message and then you burn it. Okay, this is called a one-time pad, and it's actually an old idea. I remember as a kid reading a book about codes, and they talked about how the Roman emperor, one of the Caesars, used this idea, and he had these people running with the one-time pad, and these poor guys, they had to run a lot. City to city, right? So this raises the question of, is there another way, so we use RSA encryption, this prime factorization. That's one way of sending these keys to each other through the internet, right? Well, quantum entanglement is another way, right? With quantum entanglement, what you do is you pre-share, not any keys, you pre-share a whole bunch of entangled qubits, quantum bits, and they're entangled. So what you can do is you can now do a variety of prearranged manipulations and measurements, okay? Record your results, and then transmit a message to your friend that doesn't reveal the result, it reveals certain patterns that you would expect to arise from the quantum entanglement. And then when the pattern arises as expected, you keep the data that's shared, and when the pattern doesn't arise, when you did a manipulation that your friend didn't and you got different results, you toss that bit of data. And after you do this for many, many, many entangled qubits, you build up a shared code, a shared key, without ever having to send the poor guy from Rome running to your friend's city to send it. The only thing you transmit is data about whether you shared something you didn't. So if an eavesdropper comes in and tries to steal your data, and they get this transmission, they can't figure out like what the actual bit values are. Okay, they have maybe a 50-50 chance of guessing any one. So you multiply, you have a 1,000 digit key. 1/2 to the 1,000th power is in my bad arithmetic it's 0. So there's 0 chance that they'll have the key. So this is called quantum key distribution. And now you have one-time pads that you can use to encrypt data or messages as normal. And then you can burn it and repeat. Yeah. So my understanding is that people work with light transmitted over fiber optic cable. So particles of light, they're quantum particles, and they can be entangled. So they can work as the qubits. Okay. This is something I kind of skated over in the talk. There's lots of ways. I mean, again, computation is an abstract thing that you then implement in a physical system. So even with normal computers, right? We think of like our phones and these digital devices, but before, you could implement computing with like a series of very, very intricately connected light bulbs. Anyone here know the game Minecraft? That's on a computer, right? So that's on a normal computer. Some people, because they're crazy, maybe it's one of you. It's the good kind of crazy. They implemented a computer within the digital world of Minecraft using the materials in the digital world of Minecraft that is like based on rivers flowing and gates opening and shutting in the game. It's totally wild. It's a 16-bit computer. Anyway, so the point is, to answer your question about how fast, I think it's as fast as light gets transmitted over fiber optic cable. Yeah. When we're talking about classical computing, the 0 and 1 that we talk about with these bits, as I guess I kind of mentioned, they're a physical system. So when you flip the bit, you're doing something physically. You're changing voltages across a transistor or something like that, right? In Minecraft, you're letting the river flow versus not flow. Right? And your question is, I think, so if your question is there, when you do something to a qubit, like let's say it's in the 0 state and you flip it to the 1 state, is there a change in the underlying physical reality? Is that kind of the idea? Or is it just kind of self-referential? No, it's a physical change. So if you look at the kind, how would I describe it? Yeah, okay. So in order to describe it in a physical way, I need to give you an actual physical instantiation of a qubit, right? Thankfully, they exist. As I said, Google, Amazon, IBM, all these guys, probably the US government, probably China. There are quantum computers out there. They're just not very good by computational standards, right? So Google, that's the one I know off the top of my head. I think that the graphic, by the way, for this talk, it has these two funny cats kind of superimposed over this weird chandelier-like object. That weird chandelier-like object is a Google quantum computer, or a piece of one. So if you look at that picture again, it's actually quite beautiful if you go online and you look at these things. So their quantum computers are physically based on superconducting current loops. So they have some kind of a material that can sustain an electrical current. Okay, you cool this thing way down, and it becomes a superconductor. And then it turns out that the electrical current itself can be placed in quantum superposition. So if you've got a current loop, right? If you're kind of gazing at it from like, let's say we drew one on, on the tabletop, right? You could imagine the current flowing clockwise, or counterclockwise. What was in that cola? Anyway, there's kind of two ways that it can flow. And that, once you've got two states, you've got a bit. Once you've got two states plus quantum mechanics, you've got a qubit. So once you cool this thing down and you get it flowing, you get what's called a Josephson junction. It's a superconducting implementation of a qubit, or that's at least one thing that goes into it. And basically, there's a state of energy you can, for the system that can be associated with it flowing clockwise, and another state for it flowing counterclockwise. So in flipping from the 0 to the 1, you are literally flipping the orientation of the flow. The interesting thing is, what about getting it into a superposition? Okay, and this can be done. It has to be done with care, and it's all these there's all these intricate dances with magnets that essentially one does to implement these things and to create a coherent superposition. Okay, the cooling, by the way, helps with keeping the thing coherent. Okay, because heat is the enemy of anything you want to keep with like a delicate order, right? An example of that is like certain materials can become magnetic, like a paper clip if you touch them to a permanent magnet, but then they stop being magnetic after a short time. Why? Because the air molecules bang into them, and the molecules in the paper clip jostle around, and they lose their kind of coherent orientation. You lose the magnetism. Same thing will happen to the qubit unless it's cooled down. So then once you've got it in a superposition, there are further manipulations you can do that physically change the superposition. And as long as you don't measure it, then you can actually achieve things that you wouldn't be able to do if you do insist on measuring it. So a quantum computation typically it looks like you have some qubits, they're in some initial state, let's say 0. You do various quantum manipulations to them to put them in superpositions, to entangle them. You implement your algorithm this way without any observation, just these kind of external manipulations. And at the very end, you do a measurement. And then you see, then you kind of collapse, what's called collapse the state. And you just get a string of zeros and ones coming out. But if you did it right, those zeros and ones will be the answer you were looking for. If you're not allowed to measure that the thing is in a superposition, how do you know that it's a superposition? Well, it's definitely not just a leap of faith, okay? One kind of bullheaded way of doing this is you have a mechanism that purports to put the particle in a superposition, right? That has implications for when you measure it, right? So this 0 plus 1 state that I keep going back to, right? So let's say the qubit starts in 0, and you leave it at 0, and then you measure. You're going to get 0, unless there was an error, okay? But let's assume that the thing is working ideally. If it starts in 1 and you leave it in 1, you measure it, you get 1, right? If it starts in 0 and you flip it and you measure it, you'll get 1. Okay, so that's all, just like normal computers. If you start in 0 and you supposedly put it in a superposition of 0 and 1 and you measure it, well, you're going to get a 0 or you're going to get a 1. So off of one measurement, you can't know that it worked. But if you repeat the process with the same arrangement, start at 0, do the manipulation, do the measurement, you'll build up statistics on how many times it's 0 and how many times it's 1. That's one way of testing. It's not a complete way. It's one way of testing that you've got a superposition, okay? In order to check that you really have a superposition, though, there are further tests you have to do. You have to do further manipulations, change it, and see if the statistics that you get at the end, after you do the repetition, match. And once they match the predictions of quantum theory, you go, aha, the manipulations that said they were putting it in superposition are putting it in super, right? So it's kind of a long-winded process, but that's how you do it. So the answer is, yeah, on a one-shot device, you can't actually know. But the whole point is these things should be repeatable. I mean, if a computer should be able to be reinitialized and then repeat the computation. And that's actually an important aspect of quantum algorithms as well. There's a lot of kind of repeating, iterating certain processes, and then measuring the result at the end. Yeah.
So I'm going to call on a last question from Elise in the background.
Okay. What time is it? Oh, okay. Sounds good. Go ahead, Elise. 2 questions.
And repeat them.
I will repeat them. Thanks, Greg. So one of the questions was, right now, the way I'm kind of describing these, the currently existing quantum computers are these large-scale devices. And there's a tendency to want to analogize that. So the question was, do we expect those to go in a process where they'll shrink down? The natural extension of that question is, will we have quantum computers in our pocket? Or maybe will our children or our children's children have quantum computers in their pockets? And then the other question, I'm very much not qualified to answer, which is Springfield, Massachusetts wants to be the leader in quantum technology, manufacture and development, and so on. Did I get that right? I can't speak to Springfield, so I'll take the second question first. What I can say is that Massachusetts is definitely a serious contender for one of the world's leading hubs of quantum information technology, right? You've got MIT, you've got UMass Dartmouth, you've got people all over the place studying this stuff in Massachusetts, right? And that's the thing, all you need is a big enough community of people working on these things that it kind of achieves escape velocity, to take a different form of physics, as a metaphor. So I don't know about Springfield, but I do think that Massachusetts itself is a very natural home for the development of quantum and progress in quantum technology. Your other question was, will they shrink? I think that, you know, what is it? It's a graveyard of bad predictions. What?
No.
But the short answer is probably not in the way that regular computers have shrunk, okay? It really comes down to the cooling in a lot of ways. You need pretty big machines to keep these things refrigerated so that they'll have... Maybe if we get high temperature superconductors, I don't know. I mean, there could be breakthroughs. I don't want to be arrogant and say I can see the future. But that said, I think that the model right now that people think is going to be with us for a while is that the computers themselves, the devices themselves, will be housed in certain central hubs. And then people, researchers, people designing pharmaceutical chemicals and all these other things will link up to these things, basically purchase time and remotely, kind of via the cloud, essentially run quantum computations for whatever application they want to run. So I think that that's, at least in the nearish term, the vision for these things, rather than getting them in our pocket.
Thank David for this evening's talk. And thank you to the UMass Dartmouth Physics Cheer Squad. All of the Science Cafe speakers get a Science Cafe mug, so with our thanks, thank you for this evening. I know people still have questions. I know David's willing to stay and answer them. But sort of to finish the formal part of this evening, thank you everyone for being here. This has been a great turnout for the first talk of the series. I hope to see you all next month on October 7th for our next Science Cafe talk. And that's going to be by Robert Hulsham, and he's going to speak about microclimates and how climate change is influencing the local weather. So I think that's going to be a fascinating talk. I hope to see you all on Tuesday, October 7th. Thank you all. Take care. And